Assalamu alaikum warahmatullahi wabarakatuh. Dear students, today we are going to discuss the remaining lessons from the chemical kinetics, right? In the last videos, we discussed about the how these concentrations of how this that concentrations of that species, that means reactants and products, and in a reaction mechanism intermediates also involved, so that how they are their relevant concentrations are changing with time. That thing we discussed, right? You know that the concentration of reactant is initially very high, and after that it will become lower and lower. If that is a one side reaction, that it will come to an end, right? And that product's concentration will increase with time, and it will reach a constant level because they, or if after the all the reactants are consumed up. And then when an intermediate involves in a reaction, multi-step reaction, intermediates also will be produced, so that from the beginning intermediates is not there, and after some time it will tend to increase and it will reach a higher concentration. After that it will deplete, right, and it will come to an end. Finally we cannot detect this intermediate, right? Here see that slope of this intermediate concentration is raising, but that slope is very high. That means then first step is more faster, so that quickly intermediate is produced, and after some while that intermediate tend to decrease. That means second step is slower step. First step is that faster step, and the second one is slower step. Those things we can conclude in a reaction by looking at this graph, right? And we can discuss that detailedly in this following graphs. Three types of graphs in that intermediate is involved, that are that expressed in three A, B, and C graphs, right? Then A graph we discussed, and that means the first step is faster than second step, so that quickly intermediate is formed to a higher concentration, very fast action now, so that you can reach a higher concentration of intermediate, and we can detect this intermediate by practicals, right? According to the second graph, here see that intermediate concentration is very lower, right? Lower amount of intermediate is produced in the first step, right? Initial times. Because why? That first step is the slower step in this reaction. Second step is faster than that one. So that lower amount of that intermediate is produced, right? And you can compare this one with graph A and B, right? Here see, right? And in the third graph, right? Third graph, can you see that higher amount of intermediate in this reaction? Yeah, that reactant will decrease with time, and the product will reach an amount, certain amount, but that intermediate concentration is very low. That is really equal with the last moment's intermediate concentration, step 1 and step 2. There's no that much difference between this intermediate concentration in these two steps. Lower, that means minute amount of intermediate is only produced. This means second step 2. Step 2 is very much faster, right? Very much faster than step 1. Step 1. So that only little bit that intermediate is produced, minute amount of intermediate is produced, and that will consumed up. But practically also we cannot detect this one because very lowest amount of that intermediate is produced. The B graph, first step 1 is slower. Then second step. Step 2 is faster. Step 2 is faster. Right? And this one in the graph A, step 1 is faster, so that certain amount of intermediate concentration is reached, and step 2 is step 2 slow. Right? This type of graphs with the relevant intermediate concentrations you can observe in different type of reactions. Right? Those things you have to go through the notes. Now, today we are going to discuss about cases where a pre-equilibrium exists in a mechanism, right? If the reaction has a reaction mechanism, that means it has an multi steps included. We'll see the overall reaction is A plus, for example, A plus B produces P. This is the net reaction, the overall net reaction. Overall reaction, right? A plus B come into contact to give product, right? But it happens in two steps. It is a multi-step, two-step reaction. It is a multi-step reaction. But the step 1 is the equilibrium reaction. Step 1 has an equilibrium. In that, A produces an intermediate EI, right? A produces an intermediate, but that is a reversible, right? Equilibrium reaction. That means a reversible reaction. Then I is the intermediate. Then it comes to into the action in the second step in react with B to give P. That is step 2, right? Step 2. But that's a normal one-side reaction. That is the slower step. This is a second step is the RDS. This is the RDS. Then this first step is an pre-equilibrium reaction. That means before this second step, a pre-equilibrium condition exists. A forms intermediate. That is intermediate is formed. This is a faster reaction. Fast. Right? That is the mechanism of the reaction. Then how you can write the rate laws. Right? How can you write the rate law now? Now, overall rate law R equals, so that rate for the net R for the net rate for the reaction R is equal to K into, then we have to say this relevant concentration, but we should see the RDS step. That will RDS steps, the reactants concentrations into the power will resemble with overall reactions rate. No, that thing we discussed. Now with using R, that RDS, I am reacting the rate law R equals to K into I's concentration, then to the power I's concentration and sorry, no, 10 to the power I's concentrations, 1 to the power I's concentration, because only one stoichiometry you have to see. One is the stoichiometry for this I and B's concentrations. So that also, that reaction order is rate order is 1. Because using RDS we are writing. But as we studied earlier, can we write intermediate in a rate law? We cannot write an intermediate or uncatalyzed, those things we cannot express in the rate law. so that we have to replace it, right? We cannot write here, so that I'm going to replace that one, right? I have to replace this one with how I am going to replace. That is the thing we are going to study, right? Cases where a pre-equilibrium exists. If a pre-equilibrium case exists in a reaction mechanism, how you are going to write the rate law, that is the thing we are going to discuss. Because first step is faster, second step is slower, the faster step is the reversible step, their intermediate is formed, that intermediate is reacting with another reactant to give product. Then second step is their RDS, that means lower step. Then so that overall rate low, we can write with that slower step. R equals K into I to the power 1 and B to the power 1. Then I we cannot express in the rate low because this is an intermediate, and how I can replace that one. Right? Now, for the first step, for step 1, right? For the step 1, how we can write? Then step 1 is an equilibrium reactant, so that we can write an equilibrium constant Kc that equals to I's concentration divided by A's concentration. This is the right Kc. Right, because first step is an reversible step and equilibrium step. Then this is the equilibrium constant that is Kc. Then then ice concentration, I can take this side, equals to Kc multiplied by A's concentration. I can derive an equation from this one, like this one. Right? Then instead of this ice concentration, I can put Kc into A. That one I can replace here. Now how I am going to replace that one? R equals K into, instead of the ice concentration, I can write Kc into A aqueous concentration, and I replace this I, then remaining part is B's concentrations per stored, B's concentration. And if we see this rate low, two constants are there, so that I can altogether, I can write as K dash. A's concentration, A aqueous concentration into B aqueous concentration. If we have to increase the step, we can write like this one for KCR equals K into KC means KF divided by KR. Forward reactions rate constant divided by reversible reactions rate constant. For the KC, there is another equation KF divided by KR. Forward reactions rate constant divided by reversible reactions rate constant. Then I can replace that one also. K into Kc is concentration into B's concentration. After this step, I can write, and after that I can all together, all the case, this all the case, I can resemble them. I can put K dash, A's concentration is B and B's concentration. Right, likewise, we can derive equations, but intermediates is now available in the rate law that I have replaced, but although then A is not participating in the RDS, we can take the A into the rate law, where cases that pre-equilibrium exists, right? For example, we can see some example. Here, see, another net reaction is, right, net reaction. We can see another example. I am taking this one. Then overall reaction is now, and another example, this one. This is the net reaction. Right? Then what's happening? First A plus B give the product. It's a net reaction, but in there is a fast equilibrium step and a slower step. A pre-equilibrium case also exists. In the faster step, A plus B gives an intermediate. Then intermediate reacts with another A to give P. Then in the resource bus, you have to change this number to A plus B. This is the net reaction. Net reaction is 2A plus B gives you the product. That is the net reaction. They have not put 2 in front of A. You can mark that. Now, what's happening here? Then A plus B, two A molecules to plus B molecules give B molecule give, and B molecule should give a product. But in the initial step, one A and one B gives intermediate, and another A is remaining with that A intermediate is reacting to give the product. Then overall reaction you can get like this one. Now R equals, how you can write down using the slower step. No, I'm using the slower step to write a rate law. Now R equals K into A to the power 1 and I to the power 1. But intermediate, we cannot keep this in the equation and I have to replace that. Right? How I have to replace that one now? Then for the first step 1, I can write Kc. Kc equals intermediate, that results concentration divided by reactants concentration. A's concentration, and all the stoichiometric numbers are 1 so that we are not putting any orders. B equals concentration. Right. Then instead of that I's concentration, immediate concentration, I can replace it with Kc into A's concentration multiplied by B's concentration. B's equals concentration. Then that I can replace here. That I can replace here. So instead of this I, now I am going to put this Kc into A's concentration multiplied by B's concentration. Right? Likewise, I can replace. Then what will be the equation? There is Kc, another K is there. Then instead of A's concentration, I can put A. But instead of that I's concentration, I can put Kc into A's concentration into B's concentration. Now, all together, for all the case, we can put K dash into 2 A's are coming now, and A to the power 2 and B to the power 1. Right? Likewise, we can derive an equation. Right? We can just write by looking at the reaction mechanism also. We can plot that equation easily because altogether in fast and slower step 2 A's are coming into the action. So that A to the power 2. only one B is coming to the action. So that B to the power 1. Likewise, without writing all these things, you can plot this one by just looking at the mechanism, because altogether in fast and slower steps 2A and 1B molecule is participating. We are not putting this in intermediate concentration in the rate law, so that we are omitting that one. So that R equal K dash into A to the power 2 and B to the power 1. Right? You have to practice by that using that. Another example they have given in the book. Please go through that HI, production of HI by H2 gas plus I2. You can derive an equation. And another real example also they have given, that also overall net reaction they have given, right? Another example, that NO, right? We'll go through that one. NO, this is the overall reaction. That is the net reaction. Net reaction. But in the question, they are telling observed rate law is like this one. This is the observed rate law. R equals K into NO, the second order with respect to NO gas, and first order with respect to O2 gas. But then how you can say what will be the reaction mechanism? Then if there is a pre-equilibrium case exists, you can write the first step using the rate law. 2 NO molecules and 1 O2 gas come into the action in the slower step, that means RDS. Then the reaction mechanism they have given, NO plus O2, then NO3 is the intermediate, right? NO, one NO molecule from here, right? This is a net reaction to NO plus O2 to NO2. Then they have given you like this one, rate is equal to, then observed rate according to the practical data, K into NO second order and first order with respect to that O2 gas. Then step 1 is an equilibrium reaction, NO plus 1 NO from this one NO from this first station, from NO plus 1 oxygen is producing NO plus O2, no, then NO3 comes, right? This is the fastest step. And after that NO3 is the intermediate, that is the intermediate, and it come to the action in the second step. An intermediate reacts with another NO in the reactant, so that by using the NO3 and NO2, NO2 are produced, right? Then this is the RDS. This is the slower and RDS. Then using RDS, then how you can write this rate law? Rate law now, R equal equals K into slowest in the slowest one NO3 gas is there. So that NO3 is power 1 and 1 NO is there first order with respect to that NO3 and NO. But NO3 we cannot keep in the reaction because rate low because that is an intermediate. Then how I have to replace that one? Using Kc, right? Then I can write the Kc like this one. For the first step, NO3 aqueous concentrations, result, a concentration of result solutions and divided by reactants. Now, first order divided by Kc. For this first step, I am writing Kc because that is an equilibrium. Divided NO3 divided by NO gases first order, O2 gases first order. Then instead of this NO3 is first order, I can replace this one Kc into NO gas concentration multiplied by, right, O2 gases concentration. Instead of NO3's concentration, I can write this one. Then I can replace that NO3 here with this one. This NO3, I can cut, and instead of that one, I can replace this. All three factors, Kc, NO2's concentration, O2 concentration. And then overall rate law, finally we can write now R equals K into Kc, NO2's concentration multiplied by O2 gases concentration, and there is another NO here, so another NO. Yeah. Right? Likewise, you can derive equation, right? Using this what? Pre-equilibrium cases, when pre-equilibrium cases exist, you can derive equations. You see. So that they have derived an equation for finally for the rate. There's no NO3, all K and KCs are there, so that all together they have put K dash, and in the overall reaction, in the mechanism, how many NO molecules, 2 NO molecules and 1 O2 molecule is participating. 2 NO molecules and 1 O2 molecule is participating. So that 2 to the power NO's concentration, 1 to the power O2's concentration. Likewise, instead of that intermediate concentration, you can replace that one, right? With that. Because we are in the rate law, we are not expressing this intermediate concentration, then you have to make this necessary changes by using Kc equation when a pre-equilibrium condition exists, right? Please, several examples are there. Please write and check and study how to derive the equation, because in a different condition in the exam paper they will ask. Now, today we are going to discuss about energy profiles, right? Energy diagrams. You know, by collisions of molecules that uh, by collision only that will lead to an effective collision, and then that will lead to produce more products, right? Then reactants will that they will fast, they will collide in a way that their energy is transformed one to each other. And in the first step, if they have enough sufficient energy amount to pass the activation energy barrier, then what will happen? They will pass through an state called transition state, that is called activated complex, right? Activation energy means what? The activation energy of a reaction is used to reach the transition state. Reaching the transition state does not guarantee that a reaction will proceed to products because transition state can change in either direction, right? In this case, if the new bond continues to strengthen, products form. But if the excess bonds become stronger again, the transition state reverts to reactant. So all reaction to happen, that they will pass through an activation energy barrier like this one, whether it is an exothermic or endothermic reaction like this one. They have an energy barrier between a reactant and the activated state or transition state. Transition state. If they pass, they will pass the energy barrier and they can give products. And if they, but this is transition made, there is in the transition state, a complex will be formed. There some bonds are broken and some bonds are formed, right? That is called the activated complex. Now, we will go through this graph. We will understand what I am talking about. If the reaction energy profiles they have given you for exothermic and endothermic reactions, going through a single transition one transition state. This is a one transition state. One transition state. Here see, it passes through one transition state. AB plus C produce A plus BC. That means A to B bond is broken and B to C bond is formed. Then in transition state, what will happen? It have an activated complex. This is the activated complex. Then A to B bond is broken and B to C bond is produced. Likewise, you can draw the activated complex. Right? Then energy barrier, that means the energy difference between activated state, that means transition state. This is the transition state. Transition state and the reactance is called the activation energy. Right? Then what? Then for that, I can mark that EA forward. For forward reaction, the activation energy is like this one. If the reaction is backward happens, what will happen now? Reactants are the products now. From this one, you have to measure the length between this activated TS state. That is backward reactions. This is forward reactions activates an energy. This one is slightly higher. That is backward reactions activation energy. And the energy difference between reactant and product is called delta H. Right. Likewise, the exothermic reactions energy profile they have given you. For another endothermic reactions energy profile, here see this endothermic reaction, the products has a higher energy than reactants. Now they have marked the activation energy A forward. Capital E simple A within bracket forward reaction. Here they have denoted EA backward reaction. So that will be the activation and energy will mark with reactant to activated state, this length. This is EA forward. Product to activated state is called EA backward. And delta H also you can mark. Right? This is energy. The y-axis you are plotting energy, while in the x-axis you are plotting reaction coordinate. Right? This is the energy diagram. How you will write the activated complexes, for example, we will see. Here see another example. This is the reaction. 2 NOCl, first station, the two types of reaction they have given. First one is 1 NO and O3 react to give NO2 plus O2. This is the first one. For that, they have the energy diagram they have drawn here. Then X and Y axis they have named reaction coordinate versus potential energy. Right? And reactants are NO and ozone. Product are NO2 plus O2. That thing I have marked. From reactant to that transition state energy difference, EA forward I have marked. EA backward also I have marked. Right, all together this reaction happened. That also they have marked. Likewise, you have to draw. But here see transition state, NO plus O3 will combine to give NO2. Then with NO double bond, another bond with oxygen should be formed, ozone. Oxygen atom in the ozone. Then in the ozone, one bond is broken, while with NO another one is formed. Right? Then likewise, I can give you the transition state. For the second reaction type, here see two NOCl molecules will combine together. Right? So that two NOCl molecules combine together to give chlorine. Chlorine should be formed so that it will come near. They will come closer. Right? Then NOCl, in NOCl, NCl bond is broken and ClCl bond is formed. This is the transition states complex, activated complex. We should draw properly that one, and altogether net reaction I have drawn here, and the reactants are like this one. Product is in this side. Right? I can plot the energy diagrams like that one. These are single step reactions. Transition state also I have marked. EA forward, EA backward, everything we have to mark and name the graph. For another reaction, CH3Br plus OH minus CH3OH plus Br minus. This Br is removed and OH come there. For that, then reactants, products, everything they have drawn here. Here see CH3Br. Product also I have drawn. Here see. Then transition state that is illustrated here. Then TBr carbon bromine bond is broken and carbon OH bond is formed. Carbon Br bond is broken while carbon OH bond is formed. Right? Then potential energy versus reaction coordinates, reaction overall net reaction they have drawn here. Since this is an exothermic reaction, the heat is released and the reactant is this one H3Br, and in the transition state I have drawn the transition activated complex and this product is now here. Likewise, you can draw energy diagrams. Please go through the note very carefully. Right? Those graphs are for single step reaction. In some cases, multi-step reaction we can see. Right? If that is an exothermic reaction, that heat is released and reactants are like this one, products are formed. Since this is a multiple step, so the two transition states are available. Then this is activation 1 for reactant to transition state. Length between reactant to TS is called activation energy. Length between reactant to TS. Then this is the first step's activation energy. For the second step, then one intermediate is formed by this energy barrier, right? And intermediate is formed. Then intermediate converted into product by another activation energy. That means EA2, EA forward 2. EA forward 2 means then with intermediate and energy difference between TS2, right? Then TS1 is there, TS2 is there, EA forward 1 is there, EA forward 2 is there. Since multi-step reaction, 2 energy barriers are there. This is first barrier, and now this is the right second barrier. Delta H also they have marked. By looking at the graph, another thing we can conclude, the first step's activation energy is very high. Second step activation energy is lower than first one. Then activation energy is high means barrier is higher. So that first step 1 is lower. Step 2 is faster. Another graph you can see this side. Then here the second first energy is the activation energy is this one. Right? First activation energy is reactant to TS this one. First activation. Now this is the product, this is the reactant. I is a reactive. Then this is the energy variant from intermediate to transition state. And Overall activation energy the reaction needs is EA1 plus EA2. In the second graph, we can say that second step is slower because activation energy is higher, right? Then the first one. Then two transition states they have given you. And likewise, you are plotting the graph like this one. One step is like this one, and the step is like this is an exothermic, so that heat is released. For reactant to product is the first activation energy. Second step activation energy is this one. Likewise, you can right. Up to now, we have studied all the kinetics notes in the syllabus. Please go through very carefully that the things that we have discussed. Right. With this energy diagrams, the syllabus for this kinetics and sub, we will meet you in a past paper session. Right? Inshallah. Assalamu alaikum wa rahmatullahi wa barakatuhu.